In this video, I will look one last time at throwing a brick off the top of a building, trying to get the maximum speed at the bottom. This time, we're going to add one small change. This time, we are not going to neglect air resistance. A good approach for this problem is, again, to use work and energy, but this time we'll also have to add thermal energy in. And since we don't have numbers for it, we won't use equations, so we're going to go just with using energy bar graphs to answer this question. So I've drawn it over here, and I've included a theta. So the theta, I'm going to look at two cases, the extremes. Theta could be anywhere between straight up, positive 90 degrees. It could be 0. It could be negative 90 degrees, which would be straight down. So I'm going to consider just the two extremes, straight up or straight down. Before we found that it was the same, it didn't matter. So this time we're going to use energy bar graphs. So initially, when we throw the ball, we throw the brick, it has, if gravitational potential energy is 0 at the bottom, then it has gravitational potential at the beginning. It also has kinetic energy at the beginning. At the end, it used to have only kinetic energy. Now it's got still a lot of kinetic energy, but also some thermal energy. How can we compare now to throwing straight up? So this is when we throw, that's when it hits. When we throw, the energy is the same. It's at the same height, it's at the same speed. So whatever this was, this is exactly the same. So some kinetic, some gravitational. But this time when we throw it, it's going to go up, back down, and then hit the ground. So initially we've got this. There are a couple of other interesting places along the way. What about when it reaches the top? When it reaches the top of the flight, so it was here, threw it up, it goes up and stops. No kinetic energy. So it would be all gravitational potential energy, except that we've got air resistance. The air resistance is going to be continually changing energy into thermal energy along the whole way. So gravitational and some thermal when it reaches the top. Then it comes back down. Another interesting point to look at, so you throw it up, it goes up some distance, stops, comes back down. When it gets back down to the same height, so we'll call this the throw height, still going down, but it's at that height. It'll be just like it was before. Gravitational energy is the same. Total energy is the same. It's got kinetic, but remember it lost some thermal energy here. So if there was some thermal energy here, that thermal energy can't change back to kinetic or gravitational. It is lost, you usually say. So that thermal energy is lost. More energy was converted into thermal as it came down from the top to reach the same height where you were. So actually there's probably about twice as much thermal energy at that point. Now if we look at when it hits, we've still got to get down. There will probably be about the same amount of thermal energy lost again. So now we've got this much thermal energy lost plus that much. There's a lot more thermal energy that was lost. The rest of the gravitational all converts to kinetic. But we lose a lot more kinetic energy to thermal when we throw it up. Because instead of just losing thermal on the way down, it's losing it first on the way up and then again on the way down, because it's a non-conservative force. So the best angle is to throw it straight down, and then it gets worse and worse and worse as you go up.